Okay, now we are going to learn about one of Metaheuristics algorithm, which is particle swarm optimization. Why I'm choosing particle swarm optimization for the example here? Because this is one of the most popular metaheuristic algorithm beside genetic algorithm, and I believe that if you could understand how the PSO works, so normally you can also could understand how other algorithms will work. Okay, because as I mentioned in earlier video, metaheuristic algorithm roughly have a similar flow, okay, except for the reproduction stage. Okay, so let's look at particle swarm optimization. Okay, so as introduction, PSO is proposed by Kennedy and Eberhard in 1995, and it inspired by social behavior of bird and fishes. It is combined self-experience with social experience, and this is a population-based optimization. So inspired by social behavior of bird and fishes. So if we look for the bird flocking here, okay, uh, normally the bird in this flock will follow the leaders. Okay, but of course it will have uh, some random direction, random speed, and so on. But in general, it will follow one leader. Okay. Okay. So for this example, so we want to minimize this problem. So we basically for this one we already know that the optimum solution for this problem is located at 0, 0. So if we replace x1 with 0 and x2 with 0, so we will get 0 value. So that is the most optimum solution. Okay, but for the algorithm, for the computer, okay, for the machine, we need to teach them how to find the optimum solution. Okay, so this is the search space, right? And we create a set of candidate solutions. So P1 until P5 here are the candidate solution. So this candidate solution will try to find the best possible solution. So it will move in a certain direction according to the algorithm that we use. Okay. So back to the particle swarm optimization here. Okay. So based on the existing candidate solution, so they will determine their leaders. Okay, in PSO we call it as a global best. Okay, let's say the leaders here or the global best is P2 because this one is the nearest to 0, 0. So all other solution will move towards this best solution with some random element. Okay, including the random direction for P3, maybe it's not directly going to P2, but maybe with some random factors and also the random speed. Okay, so towards the optimization process, okay, so if we can see here, this is the optimum solution that we are looking for at 0, 0. And original solution, the original position for the particle P1 until P5, and new position of P1 until P5. So if we look here, for P3, it will move towards P2 with some random element. So it's not directly going to P2, but it has some random element. Okay. For P5 also, okay, for this one, it has certain factors that influence it to move to the new position to this point. Okay, so basically we can imagine the particle swarm optimization is some sort like the movement of the particle inside the search space in order to find the optimum solution. Okay, but the difference is only between PSO and other algorithm is how the mechanism that being used, okay, to move from original position to new position, from original P2 position to new P2 position. So this is the way how the metaheuristics algorithm work. Right. Okay, so this is the basic PSO algorithm. Okay, so so it's begin with initialize the particle swarm. So this is the initialization phase. Then evaluate the fitness of each particle or calculate the fitness value. Okay, this is where we calculate and we determine the fitness of each particle. And then update individual and global best. So we update P best. This is P best is for individual best or personal best, and G best is a global best. So this is G best here is representing the leaders for each iteration. Okay, the leaders which will determine the direction of the particle moving. Okay, then update velocity and position and velocity. So this is basically the reproduction stage. So it will reproduce and then go to step 2 until termination condition met. Okay, so it will repeat with evaluating the fitness of each particle. Okay, so if the termination condition is not satisfied, so it will move or it will go to calculate the fitness actually. So it will not going to the initialization, but it will go to the fitness. Okay, evaluating the fitness. Okay, for example, okay, design a cylinder tank with 500 liters of volume. Okay, the radius R and height h should be between 0.5 and 2 meters. So now we want to design a cylinder tank. Okay, the volume must be 500 liters and the radius is radius and height between 0.5 and 2 meters. Actually, for this problem, if we just directly calculate the problem, so basically we can solve it. If, for example, in this example, we just make the radius constant, let's say 0.5, and then automatically we can calculate the required height to get the required volume. Okay, so this is just an example to show how the particle swarm optimization works for this problem. Okay, so remember for although for a simple problem, so the computer cannot think as us, so we need to teach them how they can solve this problem. Okay, for this example, we know that the cylindrical volume can be calculated by using the cylindrical area multiplied with the height of the cylinder. Okay, so the volume will be pi r square times with h. So V is equal to 500 liters, which is, if we convert into meter cubic, is 0.5 meter cubic. Okay, so now we can rephrase back this function. Okay, so V minus 0.5 equal to 0. So the objective function will be V minus 0.5. Okay, so V is pi r square times with h minus 0.5. So we put in the absolute value. So we try to minimize f. So later on, f will be minimized to the 0 value. Okay, so this is our objective function. Okay, and r and h is between 0.5 and 2.0. Right. So for the first step, which is the initialization or initialize, we create a number of random solution. The number of population here is representing the number of population that will be evaluated for each of iteration. Okay, so normally for in actual application, normally the number of population is between 20 to 40 or 20 to 50. Okay, but just for the example to show how the algorithms work, so that I only set six initial solution, or the npop, the number of population equal to 6. So the algorithm will create a random value between 0.5 and 2.0 for R and H. Okay, so these are the values. Okay, so this again, these numbers are generated randomly within the given bound. Okay, within this bound. Then this is the initialization stage. Okay, at the same time, we also define the number of iteration, the number of certain parameters, and so on in initialize phase. Then after that, we evaluate the objective function. Okay, so we calculate the objective function f by replacing the parameters value into this formula. So we will obtain f. So f here is the objective function value, or it's also called as the fitness value. Okay, so right now we want to minimize f. Okay, so based on the population that we have from P1 until P6, okay, so which one give the minimum f? Okay, so based on all the values here, the minimum f is belong to P4. Okay, P4 is for particle number 4, and 1 here is representing the number of iteration. This is the first iteration, so it will be P4 1. Okay, means that particle number 4 for the first iteration. All right, so that is the evaluation stage. The next PSO will update P best and G best. Okay, so P best is a personal best for each of solution, and global best is the overall best solution. Okay. All right. So for P-best, okay, for P-best, since this is the first iteration, means that there is no other history of the iteration earlier. So the P-best will automatically take the result from the first iteration. Okay. So this is personal best. Okay, personal best for the first iteration, because there is no other iteration before, so it will automatically take the same value as the initial solution, right? And G best is a global best, which is the overall best solution. The overall best solution, it will look at 0.1275, 1272, and R 0.78, H also 0.78. Okay, remember for P best and G best, they will keep the parameters value and also the fitness value. Okay, so because the parameters value will be utilized later on, okay, in our further calculation. All right. Then the algorithm will update velocity. Okay, so this is the PSO algorithm. So it will update the velocity using this formula. Vi represent the velocity of ith particle for j plus 1 iteration. Okay, so now when we starting to update velocity, means that j here will be 2. Okay, so omega is the initial coefficient or initial coefficient. Okay, Vij is the original velocity. Okay, C1, C2 are the coefficient. Then R1, R2 are the random numbers between 0 and 1. AP best again is the personal best, and G best is the global best, this solution. Okay, then in this example, omega C1 and C2 we can set any numbers between 1.2 until 2.0. Okay, so that's what we normally use in particle swarm optimization. Right. Okay, so this is the calculation example to update velocity. Okay, let's set our coefficient is 1.4, and let's say our random number for 1 and 2 like this. Okay, so for solution P11, so remember for solution P11, R 1.25, H 1.71. This one is taken from here. Okay, P1 and P1 solution, and also P1 fitness value. So for the first solution here, okay, is going to this one. Okay, the P best is just the same with the original solution because this is the first iteration, and we replace the value inside this formula. So omega 1.4 from this value. Okay, Vij is 1.25. So for V, we can also assume that for initial solution, V is equal to the P value. So we can do that if we don't want to create any other additional value for V for time being. Okay, then plus with C1, 1.4, R1 is the first random number. So P best, okay, P best for this particle for the first element, okay, 1.25, this one, okay, R for R, minus Pij, minus the R value, plus C2, C2 is also 1.4, R2 is the second random number. So G best is taken from, for the first particle is 1.56, okay, utilizing this formula. Then we calculate the V for H now, for the second parameter. Okay, just going through the same calculation, but we replace the value here utilizing the H parameters, and then we obtain this value. Okay, so we do the rest for the particles. And then this is for to calculate velocity. Then to calculate position, so this is the formula. So this is the new position or the new solution. Pij is the existing solution. Then Vij is the new velocity that has been calculated from this stage. Okay, and we fit in the value. So the obtained V value from earlier calculation, this one. So this is for R, this is for H. Then we replace P1R, okay, into this formula. So this is the original P value, okay, 1.25. Okay, now we are calculating for R. So this is the original value, 1.25, plus with the new velocity that had been calculated earlier, this one, 1.56. Okay, then the same thing is also for H. So we calculate 1.71, okay, from this value, plus with V value. So we will get the value for R and H for our new iteration. Right, so then we update the position based on the J value. So now this is the updated population. Okay, so this is now being noted as P12, representing P1 is the first particle, and 2 here is representing the second iteration. So we already completed the first iteration earlier, so now we move to the second iteration. Again, this is the new value for P, okay, which is the particle. So if we look for particle number 1 or P1, the new value is 2.81. So the old value P1 is 1.25. So from 1.25, now it changed to this value. The same thing is also for H. The new H is 3.72. The old H is 1.71. So now we are in the second iteration. And again, P here is representing the particle. P1 is for particle 1 and 2 here is for the number of iterations. So now for the second iteration, our P1 value are this, and for P2 this number, and so on. Okay. But if we refer back to our range that we set earlier for both R and H, it must be between 0.5 and 2.0. But some of the value are out of the bound. Okay, so we need to correct this one. Okay, so what being normally do to repair is if the value is larger than the maximum. If, for example, 2.81 here is larger than the maximum value is 2.0. So we set the value to the maximum. So we will replace this value to the maximum, which is 2.0. And if the value is less than minimum, so we set to the minimum. So for example, for P2, the R here is 0.4, which is smaller than 0.5. Okay, so we set it to minimum. Okay, so we correct back the solution into the acceptable range. Okay, so the solution will become like this. Okay, so in the solution for the second iteration will become like this. For the value that already within the bound, so we will remain that value. Then the PSO, it will repeat the procedure where it will go back to the evaluation. So now we already have the second population or the second solution for the problem, and then it will be evaluated using the similar fitness function. Okay, so means that now the algorithm will fit this value into this formula and calculate our fitness function. Okay, so when we calculate the new fitness function, so we will get the fitness value for the second iteration. So this is the fitness value for the second iteration, utilizing the new variable value that we obtained from earlier stage. Okay. Then again, it will repeat the procedure. So update P-best and G-best. Okay, so evaluate, then update P-best and G-best. So now in this stage, we already have the historical value of P-best. So this is the existing P-best. Okay, the existing P-best, this one is obtained from the first iteration, which is coming from this value. Okay, this value. This is the P-best for the first iteration. Okay, so the existing P-best, so or historical P-best, okay, will be forwarded here, forwarded to this one, and it will compare, okay, the new fitness value with the existing personal best. Okay, so if we compare for the first particle, the F for the new solution with the existing P-best, so the existing P-best is better than this one. So the P-best, the existing P-best for the first particle will be remain or will be maintained. But if we compare the fitness value, the new fitness value for P2 with the existing P-best, so the new value is better than the existing P-best, smaller than existing P-best. And for that, in that case, we update the existing P-best utilizing the new value, okay, from the second iteration. Okay, while the rest of the particles, the existing P-best is better than the new fitness. Okay, so now the updated P-best will be like this. Okay, so only P2 will be updated, okay, because it come out with a better fitness value. So this is the updated P-best for the second iteration. Okay, so now for G-best, So this is the existing GBase, okay, from the first iteration, okay, which is coming from P4, okay, this value, right? But now, if we compare the existing GBase with all of the fitness that we obtain here, so one of the fitness value is better than the existing GBase. Okay, so means that this value is nearer to the optimum solution compared with existing GBase. Okay, then we update the existing GBase. Okay, so we update the new GBase, okay, by using this solution. Okay, so when we solve the problem, when we optimize the problem, so this is among of the result that we obtain, okay, for position and cost, okay, 0.8, 0.8, so the cost is 0, 0.9, 0.9, 0.69, also the cost is 0, okay, 0.6, 1.3, cost is also 0. So if we look at the result here, okay, it will come out with different combination of parameters. And again, for the position here, the first value is representing R and the second value is representing the H. Okay, but in this solution, all of the solution are giving the 0 cost. Okay, but with different parameters combination. So this is normal in metaheuristics algorithm. So it will have different or multiple solution that come out with the minimum cost or minimum fitness function, fitness value.